In this video, I'm going to solve a few examples for the Good-ness of Fit Test problems. Recall in the last few chapters, we solved a problem for the hypothesis testing regarding a parameter of a probability distribution. And now we want to test a hypothesis regarding the entire probability distributions. So let's focus on this example right here using the Good-ness of Fit Test. Now the Good-ness of Fit Test is an inferential procedure that is used to determine whether a frequency distribution follows a specific distribution or not. Okay, so consider the first example here. A researcher wanted to determine whether bicycle death was uniformly distributed over the days of the week. So she randomly selects 200 deaths that involves a bicycle and then records the day of the week on which the deaths occur, and then obtain the following results: Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, and Saturday. And then each day has the corresponding number of the deaths, which is the frequency. Now, is there reasons to believe that the bicycle fatalities occur with equal frequency with respect to day of the week with the 0.05 level of significance, the alpha level? So can we believe that or not? So this is, of course, this is not a regular hypothesis testing as we saw from the last few chapters, but now it involves comparing each individual category here. So let's define the null hypothesis. The null hypothesis is when the bicycle fatalities have the equal frequency on each day, because we are looking to see if the bicycle death was uniformly distributed over the day. So that is what we want to check to see if that is true or not, or that is we have a high chance of believing that or not. So that is when the bicycle fatalities have the equal frequency. On each day. That means you want to see if each day do we have the same number of deaths or not. Okay, and the alternative hypothesis is when the bicycle fatalities do not have the equal frequency on each day, which is the opposite of what we assume to be true for the null hypothesis. So bicycle fatalities do not have equal frequency on each day. So the null hypothesis is just the random variable that follows a certain distribution. In this case, we are looking to see if it follows a uniform distribution or not. And the alternative hypothesis is just a random variable that does not follow the distribution in the null hypothesis, which is not having equal frequency on each day. And then our next step is to compute the test statistics. So we need to compute the test statistic before we can find a p-value. So the test statistics using the chi-square distributions, we can follow the formula, the summations, and then this is O sub I minus E sub I, the whole quantity square, divided by EI. And the I in this case is about, we have 1, 2, 3, 4, 5, 6, 7. So I will go from 1 up to 7, right? I will go from 1 all the way up to 7. 1, 2, 3, 4, 5, 6, and 7. Now this test statistics here approximately follows the chi-square distribution with the degree of freedom. Make sure we use the degree of freedom k minus 1, and we have to check for the requirement that all the expected frequencies are greater than or equal to 1 for this EI, and no more than 20% of the expected frequencies are less than 5. Alright, so we have the frequency from the data list right here, and that is your observations. And how do I find the expected value? Well, maybe I can create another column to the right here and then say this is EI, or the expected value for each of the day, Sunday through Saturday. And this expected count for each calorie here is the number of the trials of the experiment times the probability of success in the calorie. So E sub I is found by mu I, and that is the NPI. And then again, I go from 1 to 7. So this is I equal 1 all the way I to 7 to 1, 2, 3, 4, 5, 6, 7. And the N in this case, we know that this researcher selected 200 deaths. So N in this case is 200. Alright, so we know that we have N and we have PI, so you can find the expected counts for this column for each of the calorie here. Now, because you know that this is a uniform distribution, so each day has the same probability P. So the value of Pi is the same thing for P1, P2, P3, P4, P5, P7, because we assume that each day has the same frequency, or we have 7 of them, so the probability of one of the days should be 1/7. So you take Pi, which is 1/7, you multiply by N to 100, and that will give me 28.57, and that is the same thing for all the days, because we assume that the expected count for is the same for Sunday, Monday, Tuesday, and all the days, because the probabilities is the same thing if the death rate is the same. Okay, so I will write 28.57, and then the same thing, nothing is changing, because we assume that they all have the same frequency for each day. That is what we are trying to see if we can believe that or not. Okay, so after we have that, then it is ready. This is the summations, right? So you take each of the frequency. So the first one right here, I take 16. My I1, I take 16. I subtract. This is the observed value minus the expected count. So 16 OI minus the expected counts, or 28.57, and then I square that, and then I divide by the expected counts, which is 28.57, and then I do the same. I add. This is the summation. The next one, 35 minus the same thing, 28.57, and then square, and then divide by 28.57, and then I just keep going. 16, subtract that, and then you just add all of them together. So 16 minus 28.57 square divide by 28.57, and the next one is 28. And if you do all the correct calculation, you should get 19.03. That is the test statistics. And now we need to find this is the p-value for that. Alright, so we know that the degree of freedom is k minus 1, 7 minus 1, that is 6. So now let me draw the chi-square. Remember, the chi-square is non-negative, so it's always stacked from 0 and then go all the way to the right end. It is not symmetric. And as the number of the degree of freedom is increasing, then the curve is approaching to a symmetrical curve. So this is the test statistic right here, and you are looking for the area here, which is the p-value. The p-value. So we can find the p-value using the TI-84. So let's use that. Go to second, vars to get to the distribution, and then you go to the chi-square CDF. So that is the chi-square CDF. Use that function, and the lower you want that to be the test statistic we just found, which is 19.03, and then the upper you want all the way to the right, so I just put a very large positive number, so 19.03, and then 99999, and then the degree of freedom. The degree of freedom in this case should be 6 because it is k minus 1. So 6, this is the degree of freedom. So 7 minus 1 is 6. And that should give me 0.004. Around that, 0.004. And of course, this one is less than the alpha, which is 0.05. If the p-value is less than alpha, we then reject the null hypothesis. Now, if we reject the null hypothesis, if we say that, okay, I'm going to reject this guy. If I reject this guy, that means I have sufficient evidence to conclude that this thing right here, which is the bicycle fatalities, do not have equal frequency on each day. So there's enough evidence to conclude that the bicycle fatalities do not have equal frequency on each day. And that is how we apply the Good-ness of Fit Test to test for this type of problems where the distribution has several different calories, like this case here. Alright, let's take a quick look at another similar example where we apply the Good-ness of the Fit Test. A player in the craps game suspects that one of the dice is loaded. A loaded dice is one in which all the possibilities 1, 2, 3, 4, 5, and 6 are not equally likely. Now the player throws the dice 400 times, records the outcome after each throw, and then obtains the following result. So this is the number of the time, or n equal 400, and then this is the outcome 1, 2, 3, 4, 5, 6. Now again, the Good-ness of Fit Test here, we are talking about the entire probability distribution, not about a particular parameter as you saw in the last few chapters about the hypothesis testings. We are looking at the whole population, the entire probability distribution. In this case, the outcome 1, 2, 3, 4, 5, and 6, and then the frequency given here. The frequency is also called the observed value. The observed value. So again, in this case, we have to come up with the null hypothesis and the alternative hypothesis. So part A, do you think that the dice is loaded or not? The null hypothesis H0 would be the case when the die is not loaded, and the alternative hypothesis is when the die is loaded. So recall that the null hypothesis is always a statement of no difference. So there's no difference in the dice which is not loading, and the die is loaded is the other alternative hypothesis. Okay, because when the die is loaded, then all the possibilities 1, 2, 3, 4, and 5, 6 they are no longer equal to each other. So you want the one that has no difference, no change. So that is the case when the die is not loaded. So H naught is a null hypothesis. Okay, so next thing is we need to find the expected value or expected count. So that is the next column. I can also find right here, just right here. This is EI or expected counts. We have 1, 2, 3, 4, 5, 6. So the I value will go from 1, 2, 3, 4, 5, and 6 only in this case. And then again to find EI, let's do part A. EI again is PI and an N. In this case, the player throws the dice 400 times, so the N value should be 400. And what is the probability of each of the category here? 1, 2, 3, 4, 5, and 6. So again, the null hypothesis assumes that the die is not loaded. That means all the outcomes are equally likely, because before it is loaded, they are all equal, they are all the same. Number 1 has the same frequency of occurring as number 4, and number 4 has the same frequency of occurring as number 2, and so on. So every outcome has the same probability of 1 over 6. So this is PI multiplied with 400, and that will give me 66.67. And that is 66.67 for every outcome here. And the last one is the same. Alright, so we have everything, and now we are ready to apply the test statistic formula as you saw earlier. So the test statistic chi-square, again the summation of the OI, the observed value minus the expected count, square, and then EI. So I take the frequency is the observed value, 62 minus 66.67, and then square the whole thing, divide by 66.67, and then I keep adding the next one, 76 minus 66.67, square, and then divide by 66.67. And if you carry out all the calculation here, you should be able to get 4.67. And now if you draw the chi-square curve, your test statistic is 467, and we can find the p-value by using the chi-square CDF, and we go from 4.67 and then go all the way to 9999. This is the degree of freedom k-1, and then if I use my TID 84, go to second distributions and go to T chi-square CDF, I go from 4.67 and I go all the way to 99999, all the way to the right, and then the degree of freedom is 6 minus 1 is 5, so I'm able to get the area or the p-value of 0.457. 0.457. This is bigger than alpha, which is only 0.01. If the p-value is bigger than alpha, we do not reject H naught. And if we do not reject H naught, that means we don't have enough evidence to make the conclusion that the die is loaded. So there is not sufficient evidence to conclude that the die is loaded, and that answers your question A right here. And why do you think that the player might conduct the test at 0.01 level of significance rather than say 0.1 level of significance? Well, the player just does not want to make a type 1 error and incorrectly conclude that the die is loaded. And that's the answer for part B. Just remember that the significant level is the alpha level, and that will depend on the seriousness of making the type 1 error. So instead of picking 0.01, if you pick like a larger value 0.1, that means you may make a type 1 error, and if you have a type 1 error, then you incorrectly conclude that the die is loaded. So the player just does not want to make a type 1 error, so he or she doesn't want to increase the level of alpha to a larger value. Now we can also use the TI-84 and carry out all the testing, the Good-ness of Fit Test, instantly using the function provided on the TI-84, and I can show you that quickly how to do that without going through all of the hand calculation like this here. So if you go to the TI-84, again we still need to have these two columns, the expected count column and the observed value. So I go ahead and I go to Start, Edit, make sure that my L1 is my observed value, so 60, 62, 76, 76, 62, again 57, 67, and then my L2 is my expected count number, 66.67, 66.67, 66.67, 66.67, the same thing, and the last one. And then now you go out, you go to Start, and you go to the test functions, and then go to this option right here. Now the older version of TI-83 or 84 might not have this option, this functions. So if your calculator is the new TI-84, then you should be able to see the chi-square, the Good-ness of Fit Test right here. And the observed value, again, I put that in the L1 column, and the expected count is the L2 column. And then the refreedom, we have 6 of them, so 6 minus 1, that is 5. And then just click on calculate here, and you should be able to get everything you need here. You should be able to get the test statistic 0.457, and you should be able to get the p-value. No, the p-value is 0.467. The test statistic is 4.67 right here. So that is quick, and you can make the conclusion right away if we know how to perform the Good-ness of Fit Test directly on a TI-84.